This time we will use freshly squeezed lemon juice to produce, through a few interesting intermediate steps, this yellow powder, triiodomethane, also known as iodoform. So stay tuned and have fun watching. Anyone who knows this channel already knows this obligatory warning. If this is your first time here, please skip back and read it carefully. We use citric acid as a starting material for the production of iodoform. Citric acid is contained in fresh lemon juice at a concentration of 5 to 7% and can be extracted from it. To do this, we press as many fruits until we get about 100 ml of juice. In our case there are 4 pieces, we can keep the 5th to season our schnitzel dish the next day. From a chemical point of view, citric acid is 2-hydroxypropane tricarboxylic acid, which is a tribasic carboxylic acid with a hydroxy group on the middle carbon atom. The salts of which are used in the laboratory both as a buffering and a complexing agent. In the household they are used as food additives, but the acid is also used as a cleaning and rust removal agent. It's no longer produced industrially from lemons and can be obtained cheaply and freely everywhere in supermarkets and pharmacies. Our production method isn't really economically worthwhile, we only use it for the sheer joy of it. After squeezing, we try to filter out the pulp and cloudy matter by gravity, which doesn't work at all on the laboratory filter paper because the filter pores are blocked very quickly. Since we are working with real food here, we exceptionally get help with the kitchen utensils, and try again with a coffee centrifuge. We finally make it, but here too, only after the 3rd change of the filter paper. With vacuum filtration, one certainly doesn't get any further here. A centrifuge could be useful, but unfortunately we don't have one. If it were to happen again, we would probably try it in the housewife way next time, by filtering and squeezing through a clean tea towel. Finally, we got about 92.6 grams of lemon juice. In order to obtain the citric acid as pure as possible from the mixture of the numerous natural substances it contains, it must first be completely converted to the alkali tricitrate. We achieve this by adding 10% caustic soda, of which we use 30 ml as a stoichiometric equivalent for the time being, based on a rough estimate of the amount of citric acid present. The yellow coloring of the lemon juice also serves as an acid-base indicator. If it turns orange, the equivalence point has been reached. Because the color change doesn't appear at first, the acid concentration in our juice is obviously closer to the upper limit. We gradually add more caustic soda with the pipette until the said orange color appears. A total of about 36 ml of caustic soda were used, which corresponds to an acid concentration of about 7%. We check the pH of the neutralized mixture, which is now around 10. A sodium tricitrate solution of this concentration has a pH of 9. However, the slightly higher value will not significantly interfere with further use. As a result of the pH change, we filter out suspended matter again. Since gravity filtration again takes a very long time, we now switch to vacuum filtration on the Buckner funnel. Next we prepare a solution of 7 grams of anhydrous calcium chloride in about 25 ml of distilled water with magnetic stirring. This is also added to the neutralized lemon juice while stirring, whereupon sodium chloride and calcium citrate are formed in a double displacement reaction from sodium citrate and calcium chloride. Calcium citrate shows an inverse solubility. While still moderately soluble in cold water, it precipitates out in hot solution. For this reason, citric acid should not be used to descale coffee machines, dishwashers and washing machines, as it actually exacerbates the problem of clogged pipes. In our case, however, the poor solubility is the desired effect, which is why we now heat our mixture. It's then filtered off while still hot on a Buckner funnel under vacuum, and the filter cake is rinsed twice with hot distilled water. The supernatant above the white precipitate or the filtrate is no longer orange but yellowish again, which is an indication that less basic citrate is dissolved in it. We put the filter cake into a petri dish and spread it out. After it has been placed on a hot radiator to dry for several hours, the mass obtained is ground to a powder off camera in a mortar. Weighed and then transferred to a small screw top jar. We obtained 4.5 grams of calcium citrate tetrahydrate, which corresponds to a yield of about 50%. Apparently there is still a relatively large amount of citrate left in the filtrate. The next day we suspend our calcium citrate in about 25 ml of distilled water with the help of the magnetic stirrer. Then add the stoichiometric amount of 60 ml of 15% sulfuric acid. The mixture then becomes more viscous and can only be stirred magnetically at the highest level. In another double displacement reaction, the sulfuric acid releases the citric acid from the calcium citrate while it's chemically bound in calcium sulfate, better known as gypsum. This can now be filtered off. The filtrate should now contain almost pure citric acid solution. While the filtration of lemon juice progressed very sluggishly or not at all, the vacuum filtration here is an overkill. Quite a lot of precipitation is drawn into the filtrate. A second filtration on the same filter paper did not bring any improvement either, so that we finally had to resort to gravity filtration again and practice our usual patience. We use the time and prepare our reagent for the next synthesis step by trying to dissolve 2.85 grams of potassium permanganate in a good 30 ml of distilled water. Since we literally turned the solubility of the salt upside down and assumed 9 instead of a maximum of 6 grams per 100 ml of water, around 50 ml of water would actually have been needed here, as we were to notice a little later. We then add 11 ml of 15% sulfuric acid to our filtrate with the citric acid solution in a 250 ml Erlenmeyer flask and place it on the magnetic stirrer with heating function. We cap the flask with a matching double-pierced rubber stopper which houses a dropping funnel and an angled tube construction. After we had made sure that the stopcock is still closed, we fill the potassium permanganate solution into the dropping funnel and notice from the undissolved crystals, which yet now appear in the beaker, that we have incorrectly calculated the necessary amount of water. So we dissolve the permanganate decanted in the beaker in another 20 ml of distilled water and add the solution to the first portion into the dropping funnel. And this is now the entire apparatus for the following synthesis step: the oxidative decarboxylation of citric acid to acetone in a strongly acidic environment using potassium permanganate. While the acid mixture is being heated, the permanganate solution is added dropwise. The resulting acetone is immediately distilled off and collected using a cold trap in the form of a test tube in an ice water bath. This apparatus is a good makeshift solution for reactions that require slow addition to the reaction flask, but where only small amounts can be distilled and exact temperature control is not required. For larger quantities, a ground glass apparatus with a condenser should be used. Unfortunately, our existing ground joint apparatus still lacks a multi-necked flask and a dropping funnel with ground glass joint. If you want to help us so that we can buy and use such devices in the future and show the corresponding syntheses, you can do that, for example, by regularly supporting us as a patron. In return, you get exclusive access to our Patreon videos and early access to the public videos. If you want to donate us only once, you can do so via PayPal. Donors of at least 30 euros can coordinate a desired video with us and will receive a small gift from our metallurgical workshop Art of Lab. You can find the links to Patreon, PayPal and the Art of Lab product video in the video description. Returning to the decarboxylation of the citric acid, the acid mixture is first heated with magnetic stirring. Just before boiling, the stopcock is opened and the potassium permanganate solution is added dropwise. The solution should only be added little by little, otherwise the mixture would foam over. It's also important that the acid solution is already boiling when the oxidizer is added, so that acetone is actually formed. If the temperature is too low, formic acid and formaldehyde are formed instead. Both substances that you don't want in the product or in the air you breathe, in the home laboratory without a fume hood. Initially, the dripping violet solution completely decolorizes, possibly a sign of contamination of the citric acid solution with ascorbic acid, which can completely decolorize permanganate down to divalent manganese. After some time, as a result of the actual reduction with citric acid, tetravalent manganese is formed in the form of brown manganese dioxide. At the same time, a lot of carbon dioxide gas is released. A few milliliters of a volatile organic substance mixed with condensed water collect in the cooled receiver. After all the permanganate solution has been added dropwise, the stopcock is closed and the mixture is briefly continued to be heated at low heat until no more distillate comes over. In the reaction flask, all of the permanganate has been converted to manganese dioxide and the evolution of gas also slowly decreases. At the end of this operation, we get a few milliliters of an aqueous mixture of acetone and certainly some other organic byproducts. In purely mathematical terms, it should be possible to obtain about 1 gram of acetone, created by a multi-step oxidative decarboxylation of citric acid via the intermediate stages of acetone dicarboxylic acid and acetoacetic acid. Let's come to the little final, the haloform reaction of acetone with iodine in an alkaline environment. For this purpose, our condensate is heated in a water bath under temperature control to about 70 to 80 degrees Celsius. 2.5 milliliters of 10% sodium hydroxide solution are added, and finally 2 spatula tips of elemental iodine are added while stirring magnetically with a baby stir bar. Traces of iodine that stuck to the walls of the glass are rinsed into the mixture with a little distilled water from the squeeze bottle. When the iodine is added, the mixture becomes cloudy and a whitish-yellow precipitate of triiodomethane, so-called iodoform, forms. In addition to the turbidity, the disinfectant smell of the product, which is typical for hospitals and dentists, is also unmistakable. The reaction is a combination of two different reactions. In the first reaction phase, the methyl group of the methyl ketone is triple iodinated. Here the enolate form is formed via the basic aldol reaction, which attacks the electrophilic part of the iodine molecule. The second and the third halogenation of the methyl group is completely analogous. In the second reaction phase, the triiodoketone formed is actually split into carboxylic acid and iodoform. The cleavage is initiated by adding a base. The hydroxide ion attacks the carbonyl carbon, and triiodomethyl anion then splits off. This is eventually protonated to iodoform. We filter our product and rinse it off camera in the funnel with some distilled water from the squeeze bottle. We then dry it manually between filter papers and paper towels and transfer it to a small weighing pan for open final drying in a well-ventilated room. And here's a close-up of the product. The yield in relation to the calcium citrate used cannot be calculated because the amount of product obtained was below the minimum weighing amount of our scales, which means less than 70 milligrams. This also makes it clear. It's vanishingly small. As already mentioned at the beginning, none of this is economical. But we still had fun, and the proof has been provided on the proven small scale. Iodoform can be produced from lemons, even if they only supplied the methyl group, and both have little in common apart from the color they have. We hope you enjoyed it as much as we did. If so, please give us a thumbs up and leave us a subscription if you haven't already. At the top right you will find the link to our video in which we produce iodoform electrolytically. Have fun watching on our channel. See you soon, or preferably right away. Take care and goodbye.